And at this point, I think you should be comfortable doing interior and exterior angles of polygons. What you're going to find on your desk in front of you is this worksheet pack. We'll talk about this in just a moment, but what you'll find on the last page is a version of a quiz, basically. And you'll find the questions 1 through 9 are really the things we've done to this point. So this is an opportunity for you to check in and see if you've learned what you should have learned over the last few days of polygons. Now, you'll remember that we started this course with a point, the simplest shape. And then we said if we stack them together, we create a line. And then if we create a series of lines, we create a flat surface, a plane. And then we said, what can we do with lines or parts of lines? Well, we can measure them and we can name them, and we put them together to make angles, and we can measure those and we can name those. And then we put angles together to make triangles. We've studied triangles for months. We classify them. We talked about their centers, incenter, circumcenter, centroids. We found out how to prove that they're congruent to other triangles. And this is all building us towards understanding more about two-dimensional figures, and eventually we'll work into three-dimensional figures. For today, I've got a little kickoff through a slide deck here that's very silly. But as we're digging into polygons, which means 3 or more sides, we've dug into triangles already. So the next piece is going to be 4-sided figures, quadrilaterals. How many quadrilaterals do you know of? I don't know that one. What's another one? A square, rectangle, trapezoid, rhombus. What was that? Diamond, good. Those are the big ones, aren't they? So all a quadrilateral needs is it to have 4 sides that are connected at the vertices and that exist within a plane, right? That has to be all flat. So I built a little story for us here to help us remember something. Long ago, in a plane far, far away, there were shapes. Our hero, the quadrilateral, was looking for love. He tried triangles, and although some were cute, many were simply obtuse. He'd go on dates with circles, but when he tried to have a meaningful conversation, they just went on and on. And while hexagons were okay, they were just kind of regular, nothing special. But in this sea of individuals, 2 quadrilaterals found each other, fell in love, made a family, and this is their story. Appropriate for Valentine's Day coming up. Eventually, the quads were ready to have children. Despite heated debates, Papa Quad finally concaved to Mama Quad's wishes. And they took parallel pills during pregnancy. Some form of early genetic engineering, I guess. Fortunately, they had 3 beautiful children: Quad, with no parallel sides; Trap, with 1 set of parallel sides; and Para, with 2 sets of beautiful parallel sides. Each child looked like their parents and had inherited all of their attributes, but each was also special in his own way. So I use this analogy of a family to help you see a truth about quadrilaterals. The matriarch or patriarch up top here is just the generic shape of a quadrilateral. And the only attributes we'll find is that it has 4 sides, it's planar, and the sum of the angles is 360, like we talked about 2 days ago. But when we specialize that shape by either just saying that it has no parallel sides, or saying it's got exactly 1 set of parallel sides, or it's got 2 sets of parallel sides, that creates 3 individual family paths, so to speak, or branches. And if we look at the parallelograms, which is what we're digging into today, and we were to specialize it further by making either all 4 angles the same, that makes a rectangle. And a rectangle is going to not only have a bunch of cool new attributes associated with it being a rectangle, but it's going to inherit every single attribute of the parallelogram, as well as every attribute of the quadrilateral. If instead we were to take our parallelogram and not make all the angles the same to make it a rectangle, instead we were to make all the sides the same to make it a rhombus, it would come up with some new attributes, true in a rhombus, as well as the attributes of a parallelogram applying, as well as the attributes of a quadrilateral. And unfortunately, here's where my little analogy falls short, because if the square is a product of a rectangle and a rhombus, what does that mean? Aren't the rectangle and the rhombus siblings? So yeah, oh, awkward. So anyway, sorry about that. But the square does inherit everything from the rectangle, the rhombus, the parallelogram, and the other shapes. So for today, what I want to do is I want to prove to you that these two triangles are congruent. If this is a parallelogram, then when I draw a diagonal or a transversal across it, it produces two congruent triangles. And once we're able to demonstrate that that's true, you'll see that some other facts or attributes about triangles can come out. These are going to be the formations of a theorem that allows us to say, if it's a parallelogram, then certain things are true. So if we're going to make a proof, first thing we'll do is with a given. ABCD is a parallelogram with a transversal BD, given. Once we know this is parallel, transversal, what else would be helpful? Say again? Oh, the reflexive? Yeah, good. We're going to get that in just a second. But if, yeah, Marco. Excellent. We can identify that because it's a parallelogram, we have parallel lines. That's what it means to be a parallelogram definition. And now we've got parallel, transversal. And so if only we could come up with alternate interior angles, we'd have that trifecta of parallel, transversal, AIA, to say that these angle pairs are congruent. Once these angle pairs are congruent, I can bring in, as Colin suggested, the reflexive here, and then we get two triangles congruent by ASA. Once we demonstrate the triangles are congruent, we can then use CP/CTC to make a bunch of other claims. One would be that opposite angles are congruent. So here's where you guys get to just move from just listening and begin to get your notes working here. So on your notes, you'll see over on the left-hand side, it has parallelogram here. Parallelogram is a quadrilateral with blank sets of parallel sides. Two sets of parallel sides. And as we see in this picture, if we're able to demonstrate that these two triangles are congruent, what can we say about angle A and angle C? They are congruent by CP/CTC. And if we wanted to, we could do the diagonal the other way, the transversal from A to C, and we could prove that B and D are congruent. Therefore, we can say here, opposite angles are congruent. Let's jump to the bottom one. I guess I should reorganize these. If I know that these two triangles are congruent, what can I say about A, B, and CD? They're congruent. And AD and BC? Well, we know they're parallel. We said that before, but if in fact the triangles are congruent, I can say that these are congruent, right? So I can say that opposite sides are congruent. So let's put that in our notes here. Opposite sides are congruent. Now, these other two are going to require a little bit more. So in a parallelogram, what we're saying is these two are parallel. And if I treat this as a transversal, what can you say about angle 1 and angle 2?
Supplementary.
Good, they're supplementary. And because if you were like walking around the inside of a quadrilateral, these would be consecutive angles going from one to the next. We're going to call these consecutive angles. Similarly, if I did 2 to 3, now I'm talking about these red lines being the parallel lines, and this is my transversal. Aren't 2 and 3 also supplementary?
Yes.
They're same side interior angles relative to parallel lines and a transversal. So we can say up here, consecutive angles are supplementary. And then the next one is, if I were to take my parallelogram and draw in not just one transversal or diagonal, but both of them, we've already discovered that we can prove that these opposite sides are congruent. We've already said that since these lines are parallel, we can get alternate interior angles congruent. And what are these angles? Vertical. So are these two little triangles now congruent also? By angle, angle, side? Therefore, I can say that corresponding parts are also congruent. In other words, when I draw two diagonals in a parallelogram, they will perfectly bisect each other, cut each other in half. This is the fourth feature of a parallelogram. Diagonals bisect each other. These are four theorems that you'll be able to use eventually. And in fact, you're going to use them in your homework on this